Hello everyone. Welcome back to everyone at COP26 and at our hubs and also those watching virtually online. It's my pleasure to introduce Professor Mark Innall from SAMS, who's going to lead a discussion on the Atlantic overturning circulation and its stability under climate change. Take it away, Mark.
Thank you very much, everyone. Welcome, everyone. I just kept my mask on. I'm very chuffed. I've got the Nicola Sturgeon mask today, so I'm pretty pleased with that, but I shall take it off for speaking. Okay, welcome, everyone. Pleasure to welcome you to the zone here. I've got a full house here, which is great. Welcome to people online, there's the camera, and welcome to people after the event who watch this recorded. I hope there are a few of them. Welcome to my final year students if you're watching on a Saturday morning. I hope you are. Okay, so the purpose of this session today is we're going to look at, we heard in the previous session, for those of you who are here, about how interconnected the whole global ocean is. We're going to focus in today on the Atlantic and its direct effect on the Arctic Ocean. We're going to think about the fragility, complexity, and particularly the uncertainty surrounding change in the Arctic. And for that, we have to look at the whole Atlantic Ocean. We have to think about the way heat comes in around South Africa into the Atlantic Ocean, into the South Atlantic Ocean, how it then moves up into the North Atlantic Ocean and into the Arctic. It's a connected system. I don't really think of the Arctic as separate from the Atlantic. So we need to think of it as a whole system. We've got a real eclectic mix of things for you today. We've got an introduction from our the chair of the Scottish Science Advisory Council. I'll show a 2-minute introduction from Professor Maggie Gill in a second. We've then got a fabulous half-hour movie film from director Michael Schneider, who's in the audience, and will introduce the film. So I really invite you to get in the groove, get into the mood of a half-hour film. And then we'll go in to have some short presentations discussing the complexity of the science, the complexity of some of the policy-related issues, and the complexity of the biological ecosystems associated with the Arctic Ocean. And then we'll have a Q&A panel session at the end. So there will be polar bears, not just on my socks. There'll be some polar bears because you've seen the penguins already. So we're going to move on to polar bears. Anyway, I shall start just by showing a 2-minute intro from Professor Maggie Gill. I have to get manual advance here. A little bit of tech trouble. Here we go.
My name is Maggie Gill, and I am privileged to be the chair of the Scottish Science Advisory Council. The council was established by the Scottish Government to provide objective and independent advice.
Okay, I think what we might do in the interests of time, I'll invite Michael to come up on stage now. I think I'll show Maggie's introduction after the screening of Michael's film. So a pleasure to introduce Michael Schneider onto stage now, who's the director of Into the Dark, and that'll be followed by a full screening of the film. So this is different from the rapid fire information and discussion we've had up until now. This is an opportunity for you to enjoy your Saturday morning and watch a full-length documentary film about the fragility of the Arctic. Michael.
Well, good morning. Thanks for having me, and thanks for being here. My name is Mike Snyder. I'm a photographer, and I'm a filmmaker, and I'm the director of Into the Dark. And I'm a climate scientist by training, and I now run a production company that makes films really with the goal of raising scientific literacy and trying to drive impact around environmental issues. And I made this transition from science to visual storytelling because as a graduate student, I was overwhelmed by the amount that we already know about climate science and all the tools we have to resolve this issue. And despite that, particularly at the time that I was studying, just how little we were doing. So I fundamentally believe we have to tell better stories about who we are and why we're here and how to be good stewards of this planet. So for the films that I make, that's my core goal, is that they're somehow more than pretty pictures, right? They're somehow more than entertainment. They're also a call to action. And so even though I hope you enjoy the film, I hope it's a good film, an entertaining film to watch. I hope it's something more than that for you. So finally, I'd just like to say, in particular to the folks that are here doing that work, that are here working at the conference, thank you so much for that work. Thank you for being here. And please, I implore you to get it done. I fundamentally believe this is the call of our generation, and now is the time. So I have to have hope that we're going to see it through. So thank you so much for that work, and I do hope that you enjoy the film. Thanks.
While we get the film running, here it comes. pace today, and perhaps the other events and dance. We'll have we could take a couple of questions now. I'm just looking at the IT, whether we want to go, If there's any questions from the audience here, who would like to ask Michael a question, you can take one question just now. No, I had one question. I had one here. I had one question, Michael. I had one question to answer. Filming requires light. And you're into the night. So this presents challenges and also working on small moving.
Well, I have to say, this film was the largest technical challenge I've ever faced in filmmaking. Not least of which because photography, film is painting with light, and in the absence of light, you've got to get pretty creative. But I have to say that was also the draw to making the film, is to do something that would be a little bit different, that would be hard to do. In a lot of ways, we're trying to incredibly noisy, and one of the true miracles of this film is that there are engines churning in the background the entire time, and crunching through it. There's working really hard. And finally, I was truly, famously, tremendously seasick. The entire time that I was there. And in fact, shamelessly, I had a cameo. To be with such talented individuals and get to share their stories. So I felt enormously lucky to be a part of this project.
Thanks, Michael. Thank you very much. Thanks, Michael. Thank you very much.
Okay,
Thanks, Michael.
we're
Thank you
now
very much.
going
Thanks,
to
Michael.
move on
Thanks,
to
Michael. The events, we have events, and then we'll have a panel discussion afterwards. Unfortunately, I couldn't show you the Welsh address from Maggie Gill fully. However, I do know what she was going to say. She was going to point out that the IPCC AR6 report, which is what a lot of the evidence base, is that there's any median confidence that the conveyor system of heat in the Atlantic Ocean will not collapse. Hence the title of this session, Will the Arctic warm or cool? Will Glasgow turn from a dreich, windy city to something more like Boston or New York? And particularly on a day like today, we ask such questions. So it's a pleasure now to introduce Professor Stuart Cunningham from SAMS, who's going to introduce us to some of the complexity of the heat conveyor in the Atlantic Ocean and some of the uncertainty around its stability going forward. Thanks, Stuart.
Okay, thank you, Mark. Hi, everyone. Gosh, I spent 30 years at sea, and so that film was giving me goosebumps sitting watching it. So this amazing picture shows a scientific party sledging across melting sea ice in 2019. Now, these are unusual and exceptional conditions. And the question is, will we continue to see the Arctic warming, or is a cooling a possibility? So let's talk a little bit about where we are in the current global warming situation. So this shows surface air temperature change since early in the industrial era. And so really notable is the high latitude warming, particularly over the Arctic Ocean, where you see temperatures exceeding now 2.5 degrees centigrade from pre-industrial times. You see the warmth extending southwards across Canada, North America, Europe, and Eurasia. Now, over land, the average warming is already 1.5 degrees centigrade. So that's well above already the 1.5 degree target limit for the global average. And the oceans are around 0.8 degrees centigrade warmer, air temperature warmer over the oceans. So one of the big impacts of this high latitude warming is that sea ice has reduced by 30% in the Arctic, and it is projected to be absent by 2100. So this exposes the dark ocean to absorbing solar energy, and so that will continue to accelerate global warming. So the current pattern is, will we see a continuing change, a pattern amplification of this, so continued global warming at a steady rate proportional to the atmospheric CO2 concentrations? Will it just be reflected as a pattern amplification of this type of warming situation? But there are low probability, high impact events, tipping points in the climate system that can make changes happen much more rapidly than the forcing is occurring. And this plot shows a recent result from the UK Met Office climate model, where they artificially halt the Atlantic Meridional overturning circulation by adding fresh water to the North Atlantic. And the overturning is carrying heat northwards. And if you switch it off by triggering this feedback in the climate system, you see a rather abrupt cooling over the whole of the Northern Hemisphere. Over the UK, for example, temperatures would be forecast to drop by 5 degrees centigrade. And as Mark said, we know that the IPCC say there is only a medium likelihood that this could occur. So it's not a low likelihood. I mean, we just don't have enough knowledge. But we do know that in the past climate record, these abrupt changes have happened many times before. And in fact, in the recent past, about 8,200 years ago, after we had come out of the last ice age, an ice dam burst in where all the meltwater was being held back, and the Atlantic was abruptly flooded with fresh water. And that basically switched off this Atlantic circulation and led to a rather rapid and abrupt and extensive cooling throughout the Northern Hemisphere, North America, Europe, and in Asia. So what is it about the Atlantic circulation that's driving that? This is a really nice map. You've seen it a few times in the last session. And what I like about it is it's really focusing on the ocean. And in particular, it shows how the Arctic Ocean is connected through the Atlantic Ocean to the Pacific and Indian via the Southern Ocean. Okay? And in the blue and red lines, we have this thing called the conveyor belt, which you will have heard about. And the red lines, especially focusing on the North Atlantic, is warm water moving all the way north through the Atlantic into the Arctic. And then the blue line is the cold, deep water returning south. And it's this circulation that is affecting the heat transport that's giving us our current climate. But the connection between the red upper limb and the blue lower limb happens in special places. So in the Arctic Ocean and in that region between Greenland and Scotland, they're particularly important regions where warm water is converted into deep water. But that is being impacted by Greenland melt, by sea ice melt, and by increasing river flows from the Eurasian rivers. And fresh water makes it much harder to convert upper ocean water to the deep water. And at the moment, this excess of fresh water is being taken out of the Atlantic and the Arctic system by this global conveyor belt, and it's being exported to the global ocean. But there comes a point when the Atlantic is no longer exporting enough of the excess fresh water, meltwater, that it just stops the circulation, and you can drive the climate into one of these tipping points. So that's a feedback in the climate system. Now, we're going to have a quick look at a movie. This is some research that's being done in Scotland to try and understand these complex feedbacks between Greenland ice in particular and the Atlantic Ocean circulation. And this is going to show a state-of-the-art computer model of Atlantic water entering a fjord, melting the fjord, and the fresh water feeding back into the Atlantic circulation.
Hi, I'm Neil Fraser, an oceanographer at SAMS. In this video, we'll explore how ocean dynamics can drive warm water into Arctic fjords, where it accelerates the melting of glaciers and sea ice. This is a simulation of kangaroo slap fjord in southeast Greenland, the adjacent shelf region, Here we can see warm water flowing towards the entrance and now we can see the interface between this warm water and the colder, fresher water above. It's waves in this interface which pump warm water into the fjord. From this perspective, we can see how strong winds drive very large waves. We therefore get strong currents in the fjord whenever we have stormy weather. The warm water flows right to the end of the fjord, to the left of the picture here, where it comes into direct contact with the glacier face below the surface. This means significant melting can occur during the winter when winds are strongest. Similar processes occur in Svalbard, where changes in the wind patterns lead to increased warm water entering the fjord.
Animation. I don't know if we're making the versions of our talks available afterwards, but there are narrated versions that I could give to people if they wanted to hear the full thing. So this was supposed to illustrate the complex feedbacks you get between the Atlantic circulation and the glaciers in Greenland. And so the Atlantic circulation is melting the ice, the fresh water comes back into the Atlantic, and that's one of these processes that can drive us through climate tipping points. So just to get towards the end of my talk, this is from the IPCC. It shows the air temperature, global temperature change in the last 2,000 years. Okay, and we really see how we're driving warmth in the recent period, and it's exceptional over those 2,000 years. And we also know that we're now in the warmest multi-century period in the last 100,000 years. So this kind of highlights that we're really forcing the climate through a change that has been unprecedented in the natural system. So this is what we're talking about, two possibilities. On the left-hand side of the plot, we have a continued warming of the climate, the pattern amplification I was talking about. So the Arctic is continuing to warm, but with more energy in the climate system. And that's what's supposed to be illustrated there on the left. But we can drive the climate through a tipping point, an abrupt tipping point, and it goes into a new state, and that new state might be a much colder Arctic, and it might be one that the Arctic finds very difficult to get out of in the future, because we know that even if we stop the melting, it's possible that the climate remains in that much colder state. So to conclude this talk, abrupt climate change is observed many times in the climate record and is a serious scientific challenge to understand and predict. Abrupt climate change poses risks to the mitigation strategies we adopt because of its inherent unpredictability and because of the rates of change. And the uncertainties of hitting tipping points and the societal risks that they pose are such that we should mitigate climate change and do all that is possible to limit global warming. Thank you.
Thank you, Stuart. Very clear exposition of the unlikely but highly impactful event of a regime shift or a tipping point shift in the Atlantic Ocean and in the global ocean. We are going to move now. I first have to give an apology. I'm going to apologize to Dr. Marilena Altmans and Dr. Maria Paz Chidichimo, who I did have pre-records from, and I was going to show now. And they were going to show you how we observe the Atlantic Ocean system. Unfortunately, due to technical hitches and lots of feedback, we're not going to show those, but we will be able to make them available somehow to you. Anyway, now it gives me great pleasure to introduce a movie star onto stage, but actually he's also a physicist and at a local university, Strathclyde University. So, Dave.
Thanks very much. So, I've got about 4 minutes to tell you a wee bit about light and life in the Arctic Ocean. You've seen in the movie there how the Arctic Ocean looks during winter when we have the long periods of darkness. But we went back up again later in the year, and we saw scenes like this, where you see the long summer day of 6 months of daylight, and this is the midnight sun shining on an ice-covered Arctic. And light has a hugely important role to play in driving photosynthesis in the Arctic Ocean, and it drives animal behaviour as well. And I'm interested in the light getting down actually into the ocean itself. So we have this huge seasonality that's characteristic of polar regions in the light cycle. And in terms of what actually gets into the ocean itself, it's all mediated by the presence or absence of sea ice and snow. So what I want to talk about very briefly is how that impacts on the Arctic food web. So here we have a really nice image of the various trophic levels of the Arctic food web. You see it starts with phytoplankton and ice algae at the base of the food web, and then everything else stems from that. We have zooplankton eating the phytoplankton. The zooplankton are then eaten by everything from the cod, the whales, the seabirds, and that goes up through the food chain to the iconic species of polar bears and humans as well. So the entire system is driven by that photosynthesis, and those small microscopic plants support all of the animal life in the ocean. So I want to look at two scenarios. In the first one, we have an ice-covered ocean where we have sea ice on the sea surface. Now that makes the ocean a little bit darker, and you might imagine that means you've got less plant growth. But what actually happens is that the ice provides a nice stable substrate for ice algae to form on the underside. And these ice algae are therefore able to bloom really early in the season, and they provide really good nutritional content. So if you're a poor wee zooplankton that's struggling to make it through this long, dark Arctic winter, this is the first new food source that you get, and it's really important for your life cycle that you can get access to this. In a situation where we see more melting and we end up with more open water, we're going to see production of pelagic phytoplankton, and they will tend to bloom later because you don't have that ice cover anymore. You get wind mixing, which makes it much harder to form stable water column to get blooms forming. So that means that the zooplankton will have to wait longer in order to get this first fresh meal, and the phytoplankton that are produced under these circumstances are typically less nutritious. So in many cases, this might be too little, too late for hungry zooplankton that are desperately waiting for this fresh source of nutrition. What you find is that the zooplankton have a life cycle that's really tuned into the timing and availability of this plant material. So we put them at jeopardy in a situation where the reliable ice algae early on in the season becomes less available. And whatever happens to the zooplankton feeds all the way through this ecosystem. As we say, there are links from the zooplankton all the way up through the whales, the seals, up through the polar bears and the seabirds, up to humans as well. So what happens at these early stages of the food cycle has impacts right throughout the ecosystem. So Stuart has just been talking about the uncertainty that we have in what will happen to Arctic ecosystems in the future. What we see here, when we think about life in the Arctic Ocean, we think about these iconic species. And I guess the message I just want to get across is that polar bears, seals, walruses are ultimately dependent on the zooplankton, the phytoplankton. That comes down to the ice levels and the light levels. And in an uncertain future, we are working really hard to try and understand what the future holds for these species. But there are a huge number of outstanding uncertainties. That means that despite the fact that we're just part of a real global effort to understand these feedback processes, there's still a lot of unknowns that we are working hard to understand. But a situation such as what Stuart has described is really a massive challenge to the survival of these kinds of species. So thank you very much.
Thank you, Dave. Finally, it's a great pleasure to introduce Dr. B. Burks from Marine Scotland Science. And B is going to give, I think, there's a huge impact. We've talked about, will the Arctic warm or cool? What does that mean for infrastructure, for fisheries, for flooding, for all these parts that the government have to worry about? Now, B is a scientist in her own right, but she does work for Marine Scotland, and she is part of the Scottish Government. And I hope that B is going to be able to give us some perspective on these issues from the Scottish Government perspective at any rate, but probably more widely. Thank you, B.
Okay, whilst Heidi's giving me the signal that my slides are coming. So my name's Bea Burks. I'm a scientist working for Scottish Government in their Marine Directorate called Marine Scotland. And I'm going to talk about how we advise policymakers to really try and deal with this uncertainty. And I am hoping, oh, there they are. Okay, great. So knowledge to climate action, and really I'm a knowledge translator working in government. Stuart's already shown these. They're warming stripes. They were made famous by the University of Reading and Ed Hawkins, and hopefully you'll have seen them around the conference already. And what these really highlight for me is at the top we have the global warming stripes. So they really show the long-term trend of global warming due to human activities. In the middle, we have the Scottish air temperature, and you can see there's a lot more variability, but there's still an overarching warming trend. And in the bottom panel, we have the water temperatures of Atlantic water in Scottish waters, just offshore Glasgow here. So if you head into the open ocean, and it really shows that the ocean has a larger memory, and it has these great swings of very warm and very cold or colder periods, relatively speaking. And that means that when we communicate to policymakers, we really have to highlight that just because temperatures are maybe more variable where they're based, it does not mean that the global warming signal is not important and that we shouldn't be taking climate action. So the panel on the left here shows a timeline of climate policies in recent years. So it starts with 1988, when the first IPCC was established. And in 1990, the first assessment report was actually published. But this timeline also shows there's latency in the system between establishing a scientific evidence base and then successfully communicating that into policy. So Scotland is one of the first nations, subnational governments to recognize the climate emergency, and we're really committed to meeting a net zero target by 2045. But our first climate change act was not until 2009, so that's a good few decades after the IPCC already established their first reporting cycle. And in the back of this is the panel on the right, which is the greenhouse gas emissions in the atmosphere. And so you can see that despite an increasing evidence base, we've really lacked ability to take action and reduce our emissions successfully. And part of that is that we also need information at regional scales. We need to be able to communicate at a global level what's happening, and the impacts in the Arctic are very important there, but also translate to our policy stakeholders and industry sectors what that means in the local environment. And so these are all warming stripes, but for different areas of Scottish waters. And you can see there's some coherence. So the top panels, the top half is pretty much everything on the west coast of Scotland, and the bottom part is everything that's more into the North Sea. And so you can see that there's some commonalities between those, but there are also regional differences. And that means that the impacts on the ecosystem in these two regions is also somewhat different. And we need to be able to communicate that. And the IPCC has recognized that they need to be providing much more information at the regional level to support governments to make their decisions on adaptation. And as Stuart already highlighted, there's also uncertainty in the system. If there is Arctic cooling or cooling in the subpolar North Atlantic, what does that mean for our sectors? And it is not just the marine sectors necessarily that will be impacted. The bottom left two maps show what happens to rainfall in the UK under either smooth climate change or a sudden collapse of the AMOC. And what you can see is that there is a very strong drying, which means that arable farming is actually at risk. And so we need to communicate both with our own Marine Directorate, but also with policymakers in other areas of government who are trying to adapt to climate change, the importance of the ocean. And as part of that, our project, we have a project proposal currently under review with the European Commission to try and get information about the Atlantic Meridional Overturning circulation as soon as possible, ASAP, into policymakers' hands so they can really use that to inform decision-making when it comes to the blue economy, so sectors like fisheries, aquaculture, and marine renewables, but also other areas of government. And that really means that we need to make predictions, which are from days to weeks, into climate projections. And in that intervening period, there's actually a good area of, on a decade scale, where we can use forecasting quite well as well. And I'll come to that in a minute. Against that backdrop of that timeline is also the governance structure, which goes from a daily parliamentary meeting almost to elections on multi-year timescales. And I've removed one slide, sorry. What I was going to say is that the Atlantic is actually very predictable. The information we have from the Atlantic overturning circulation means that we can make predictions very well for Northern Europe, and we should really leverage that to inform policymakers. So with that, I'll show you a nice picture off of Mull, which is just one of the islands here close to Glasgow. And thank you very much.
Thanks, Bea. Thank you very much indeed. It's really informative, I think, to see, we are all, I think, familiar with the climate strikes for the globe. But I think when you drill down to the regional level, we see some very, very different patterns. And again, that's very much part of the theme we're trying to expose today about these very different, very divergent potential scenarios. Great. Well, thanks, speakers. I apologize again for those whose pre-records we were unable to show. We're going to have a Q&A now. So whilst we get the panelists up on stage, including Mike, think about your questions. So I'll take questions from the audience. I've got some questions that have come in through social media over the last week or so. I'm wondering whether we are able to have Marilena join us. So Dr. Marilena Altmans, who is oceanographer at the National Oceanography Centre in Southampton. And apologies we couldn't show her short clip, but I can, in 30 seconds, perhaps try to summarize. What we all require to do is to have some level of prediction of our climate system. And without measuring it, there is no way we can predict it. And Marilena and Maria Paz were going to show to you the observing systems right across the Atlantic Ocean, multinational, multi-year efforts that take place to measure. And there's Marilena there. Thank you, Marilena, and apologies for the technicals.
No problem. Hi.
Can we hear you?
Great.
We're good to go. We're good to go. Right. I'm actually going to start with a question for you, Marilena, because we couldn't play your piece. So I did have a question came in yesterday. Yeah, so someone was asking whether we can already see a slowdown or can we see a change in the Atlantic heat supply or the heat engine to the Arctic? Is that already evident in the observations?
Oh, this is a really good question. Yeah, so the problem with the AMOC is, or with observing the AMOC, this Atlantic Meridional Overturning circulation that transports heat northward, is that it varies on a range of timescales, and particularly on decadal timescales. So it has periods of, we see periods, alternating periods of warm phases of the North Atlantic and cold phases of the subpolar North Atlantic. And those occurred naturally in the past. So we have a natural cycle of AMOC variability, and that has been driven in the past by freshwater releases from the Arctic. So we actually have also natural freshwater releases from the Arctic, and they modulate this global overturning, or at least the North Atlantic part of the overturning circulation. And in the past, now on this natural cycle, we have increased melting, so increased freshwater influence from melting, and this is an additional effect on this circulation, but it's a different effect. So we can have more freshwater either because of more melting, or because we have more freshwater in the currents, or we can have a change of the currents. And this change of the currents, this is a natural cycle, and this change of freshwater in the currents is an additional effect that is due to the global warming. And this has not led to so we don't have a trend on top of a natural cycle, but the trend has interfered with this natural cycle. And the natural cycle, the natural freshwater release, has buffered some of the influences that we have seen from increased melting. So this makes it really hard to detect influences. But one of the things it has done, it has led to an increase in the frequency and the amplitude of this cycle. So we see basically more extremes in shorter periods of time. So this is an effect that we're currently already seeing. But it's hard to say whether this is how this will continue. And it's also still, there are a lot of different observational programs. We're still working on this, and it's so it's difficult to say if it has already slowed down, but this may also not be the important question, because if we have an increase in the cycle itself, this already leads to a lot of effects on European climate and also other parts of the world.
Great, thank you, Marilena. Do we have any questions here? We'll take this question first, and then we have another question here.
I actually have two questions, if you don't mind. My first is for Dr. McKee about the under ice algae. So there's good evidence that sea ice is thinning, and maybe even the snow depth is decreasing. So there's probably more light making it to the base of the ice, the ice-ocean interface. Do the algae like that? Like, I've seen pictures of them, and they're often quite brown. Are they photosynthesizers? So are they doing better where they exist? Although obviously the ice is retreating, so there's less coverage. But are they enjoying sea ice thinning?
They may do for a short period, and then when the ice goes, then their habitat is effectively gone with it. And at that stage, you've flipped into that different stage. So I think there's a kind of general situation of who's going to be winners and who's going to be losers. It's very hard to say. It varies on different timescales, and I think one of the things that we're hearing here is that as you put the system into periods of rapid changes, you're putting stresses on all of those different layers, and it's very hard to know what the answering that question is going to depend on what timescale you're thinking of. It's a hard one.
Because, sorry, I'd like to move to the next question. I'll come back to you if we don't have another one. So, please. No, you need to.
Right. Okay, this is to B and Stuart. It's about the warming stripes. You can see a different structure to the west and east of Scotland, much simpler response to the east. Is that because of a North Atlantic current imprint, or is it atmospherically blocking atmospheric variability imprinting itself on there?
So the answer, I think, there is probably that the North Sea responds very differently. It's a shallow sea, and it's much more atmospherically influenced. So we are seeing a stronger relationship, I think, in the North Sea to the atmospheric signal than we are on the west of Scotland, which is very much dominated by that Atlantic signal. And I don't know, Stuart, if you would like to add anything. No? Okay, great. Thank you.
Okay, I am being given the time is up signal from the back desk. So I think we can carry on this discussion. We're all here, so please come and talk to us afterwards online. If there's a way to post questions, please do, and we'll do our best to answer them. I just want to thank everyone, thank the speakers. Thank you to Michael for the film, and I hope you enjoyed that. I hope it gave you a piece of peace within the chaos of COP26 Blue Zone, which I can assure you, if you're here, it's quite chaotic, but it's wonderful. And I hope we've given you some sense of the complexity of the North Atlantic and how there are some very, very different potential outcomes for the Arctic. So it's not necessarily going to get warmer, and the uncertainty is huge, and we need to continue to observe and predict if we're going to get anywhere near understanding if and when we might reach such a tipping point. Thank you, everyone. Goodbye.